Scientific notation, written and presented by me, Jean Legui. Here's the legal stuff. Okay, scientific notation is used as a shorthand way of dealing with very big or very small numbers. Big numbers like this, which is an estimate of the number of grains of sand on all the world's beaches, which is, well, it's a big number. Or very small numbers like this, which is the probability of winning the lotto, where 1 is certainty, so that's the fractional probability. Okay, so scientific notation makes it easier to deal with those types of numbers. Okay, so let's have a go at making this very big unwieldy number something a little bit more friendly using scientific notation. First thing you do is you rewrite the number with the decimal point to the right of the first non-zero digit. And the first non-zero digit is this 5. So I rewrite it 5.6. Next, I find the decimal point in the original number and I count how many places I need to shift it to get 5.6. So in the original number, decimal point's there. So I'm going to shift it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 places. 21 places in that direction. Then what I do is I write times 10 to the power of count, where count is how many places I shifted it, and because I went right to left, it's a positive number. So I get 5.6 times 10 to the power of 21. The 21 bit, that's called the exponent. Now you've got to admit that's a lot easier to write than the big number we started with. Okay, let's see what we can do with a really small number, which was the lotto win. First thing we do is we rewrite the number with the decimal point to the right of the first non-zero digit. Now in this case, the first non-zero digit we see is that 2 there. So we rewrite it 2.205. Then we find the decimal point in the original and count how many places we need to shift it to get to the new number. So there's the decimal place. We go 1, 2, 3, 4, 5, 6, 7, 8. And we went that way by 8. So we now write times 10 to the power of how many we shifted it, which was 8. Now we went left to right, so it's negative 2.205 times 10 to the power of minus 8. Once again, easier to write. The rule to remember is when you go right to left, it's positive. When you go left to right, it's negative. Positive ones are for big numbers, negative ones are for little numbers. Okay, let's have another example. Big number, Avogadro's number. That's the number of atoms in 12 grams of carbon. And there it is for you. There is a lot of atoms in 12 grams of carbon. So, we rewrite it with 1 digit to the left of the decimal point, or the decimal point just to the right of the first digit. So that gives us the 6.02 here. 6.02214113. Now, we count how many places we needed to shift it. The original decimal point was there, so we shift it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And then we write down times 10 to the power of 23, because I shifted it that way, so it's positive, and I shifted it by 23. Small number now, the mass of an electron in kilograms. We find the first decimal point, the first non-zero digit, and bung the decimal point to the right of it. So that's just here. See, just there. That's the 9, first non-zero one we got. And then we count how many times we need to shift the decimal point to get there. So we start from here and we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 26, 27, 28, 29, 30, 31. So we went that way by 31. And because we went that way, it's negative, and we got times 10 to the minus 31. A lot easier to deal with. Okay, now supposing we want to go the other way, we got a scientific notation, number in scientific notation, and we want to open it up. Here's the charge on an electron, 1.6 times 10 to the minus 19 coulombs. Now what we're going to do is we're going to shift that decimal point. In fact, we're going to shift it 19 that way. And we're going that way because it's minus. So we're going, it's opposite of what we did before. So we've got 1.6, it started there. We're going to go, don't do that. 1.6, it started there. I'm going to go 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So the decimal point is going to end up there. Now, what I do here is I've got zeros missing here, so I just put them in. Just for the sake of completion, there we go. So that's going the other way. I just pointed it along 19. Here's another one, the mass of the Earth in kilograms. 5.97219 times 10 to the 12 kilograms. A very big number. So I write it out, and then I figure out how many times I need to shift the decimal point. I'm going to go this way. I'm going to go this way this time because it's positive and it's a big number. I started there, 5.9. Don't do that. Started there, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I just put the zeros in. So that's going the other way. A very big number in kilograms, as you probably expect. Now, where scientific notation comes really useful is when we're doing sums with really big numbers. Let's take that calculation to find the number of grains of sand in the world. Now, there's a few assumptions here. Firstly, I kind of assume that there are 8,000 grains of sand per cubic centimetre. So to find the number per cubic metre, I'd multiply that by 100 times 100 times 100, because a cubic centimetre, when you make that into a cubic metre, there's 100 of them going that way, and then there's 100 of them going that way, and then there's 100 of them going that way, to give me a cubic metre. 100. Okay, so to find in cubic metres, you take 8,000 times 100 times 100 times 100. I'll put all of those into scientific notation, which gives me 8 times 10 to the 3 times 1 times 10 to the 2 times 1 times 10 to the 2 times 1 times 10 to the 2. Now, the beauty of scientific notation is that all you have to do is multiply the numbers. So 8 times 1 times 1. 8 times 1 times 1, which equals 8. And then add the exponents. 3, 4, 5, 6, 7, 8, 9. So that gives me 8 times 10 to the 9 grams per cubic metre. So once again, you multiply the numbers and add the exponents. And that's easy. That makes life a lot easier. So let's assume that the average beach is 50 metres wide and 25 metres deep, and that there are 560 million meters of beach in the world. Now this is taken from a online, there's a fellow called the Maths Dude did these estimates. If we assume that, then to work out the number of grains of sand, we first need to find how many cubic meters of beach there are. So we take the 5.6 million and, or sorry, 560 million, and that's 5.6 times 10 to the 8. And we multiply that by 5 times 10 to the 1, which is the 50 meters, times 2.5 times 10 to the 1, which is the 25 meters. And what we do is we multiply 5.6 with 5 and 2.5, and then we add the exponents, 8, 9, 10. So multiplying 5.6 by 5 by 2.5 gives me 70, and then that gives me 8, 9, 10. That gives me my 10 here. Now, that's 70 times 10, so I'm going to shift it one more across, doink, and make that 71. Sorry, make that 7.0 times 10 to the 11. So I shifted it 1, that becomes 11, and it becomes scientific notation. Now this is the number of grains of sand. Here are the grains of sand. Grains per cubic meter, and this is the number of cubic meters. Multiplying those two together, the cubic meters cancel out and we just end up with grains. So we multiply 8 by 7 and we add the exponents. And 8 by 7 is 56. 11 plus 9 is 20. We shift it one more across, badoink, and make that 5.6 and 21. That's where scientific notation becomes really useful. A lot of sums becomes really, really easy. And that's the end of that.